to introduce Nunes Amaral. I'm not going to go through bios because we already have those in the brochure that you can take a look at. And this particular session has two speakers, Nunes and followed by Tim. And this is generally in the area of understanding the differences between network web science on the one hand and engineering networks or engineering the web. So it's on that general theme. You want to talk?
So actually, let me try to start this, because why should we waste too much time? I have to apologize for something. I'm not really a morning person, so I will hope not be kicking myself or someone, because I'm usually in a terrible mood in the morning. And now I don't have slides. So Nunes asked me to talk about this aspect and balance between sort of understanding and making a science of the web or of social systems and contrasting it with engineering. So this is not a topic on which I usually talk about. And so I will try to set this in sort of broader terms. And I think one of the ideas, and this was something that he alluded to in his introduction, was, do we need theory? Do we need understanding when we have all of this data? Can't we just go about trying to do things in a heuristic way and make sense of them in that way? And my answer, just to give away to this question, is that no, we need theory. I mean, actually, the fact that we have lots and lots of data without a theory just means that the risk that we find something that is actually meaningless is greater, right? The more data you have, the more likely it is that you find something that looks abnormal, exciting, interesting, and may turn out just to be an anomaly. And so I think that theory and developing, if not a theory of what's going on in the system, but null models against which to test the data that we have on a system is extremely important, because that's how you are going to get to an understanding of what may be at play in the system that you are studying. And you may be able to develop an understanding of your system. Now, for much of the development of science, the way in which we would go about studying a system and making sense of it was relatively straightforward, right? You would carve out a piece of your system. You would try to get it to the limit in which the rest of the universe is interacting very weakly with the part of your system that you are interested, and then just kind of make sense of that small piece of reality. You know, a few years ago, there was a very interesting article published by a molecular biologist that was written, "How will a molecular biologist fix a radio?" I don't know how many of you have ever read that article. You have? Anyone else? I'll give a little summary. It goes about it more or less like this. So a molecular biologist has the bad luck of having a broken radio. So he decides to use the scientific method to fix it. So he goes about, he writes an NIH grant and obtains funds to buy 1,000 radios, identical to the one that is broken. He also buys a few shotguns and some bullets. And then he proceeds to shoot every single radio. And then he opens the radio and looks at the inside. And in the inside, he finds all these little pieces. And he says, okay, I have red pieces, I have blue pieces, I have circular red pieces, I have triangular black pieces. And then he tries to see, close it again, see, does the radio work or not? And, you know, if the radio does not work, he figures out, okay, my bullet hit some crucial part of the radio. So he goes back again, and it looks at two radios, one that works and one that does not work, and looks, oh, this one seems to have this piece broken and this one doesn't. So then he identifies the things that are crucial for the radio to work. And he starts doing this. Now, because he was lucky enough to get NIH funding to buy radios and shotguns and bullets, lots of other molecular biologists get really excited about the possibility of buying radios and shotguns and bullets. And so they are all doing the same experiment. And because they cannot understand the fact that this radio has tens of thousands of pieces, and they want to make sense of it, the first molecular biologist decides that there is this particular component to which he comes up with a cool acronym like MIC, the most important component, and says, this is how this system works. Without this MIC, the radio does not work. But then another molecular biologist finds another piece that is different. And the radio also does not work in that case. So now they give it a new name. The truly, truly important component, TTIC. And people will go off talks about MIC and TTIC and have fights about which one is really the important one. Now, this is sort of a look at the system without understanding truly what is going on and looking from among a ton of stuff. Oh, I have this again. Okay. And the remote is working? Of course, now I have no notion of how much time I've spent or where I was supposed to be in the original talk. But the point is, if you don't go in thinking about how to make sense of what you are finding, you may be having this big fight about what is important, what is not important, and looking at these systems as if they are composed of completely independent and separate parts, instead of understanding them as a whole, and the fact that lots of things have to work together for the system to accomplish its function. And this is the thing that makes it so difficult, is that it's really hard to look at the whole of it and make sense of it. And so this is, I think, the challenge. And my talk was about discover, understand, and engineer, was a sequence that we like to go through. And in many cases, systems that probably we studied for several centuries up to the more recent decades, the path along that path was relatively straightforward. But right now, we are dealing with systems that are so interconnected and for which it's so hard to break them into pieces that each of the steps is becoming extraordinarily difficult. So the problem really many times is it's not in systems like this, it's not easy to know where to look to start making sense of the system. And one thing that I think is very promising and hopeful is the fact that simultaneously we are also getting tremendous amounts of information. And tremendous amount of information, if we look at them blindly, may misguide us, but can also be extremely important in terms of discovering things that are going on, things that you'd like to understand. And one of my favorite examples is actually the Framingham heart study. This was a study in which Framingham is a small town city in Massachusetts, and they studied about 5,200 people over decades. They got information about blood pressure, cholesterol, eating habits, diet, exercising, all of this stuff. And things that right now we all take as a given that we know about cardiovascular disease were actually all discovered by this study. Until the 1960s, people didn't know about cigarette smoking increasing the risk of heart disease. They didn't know about cholesterol levels, blood pressure as kind of indicators of risks for cardiac disease. Things that we now take for granted were all discovered very, very recently. And they were discovered because people had the possibility of studying these large numbers of people over long periods of time. So I think that this is the excitement about many of these new areas, is that now we have very complex systems that depend on many, many parameters, but we also have huge amounts of data. And if we look at them the right way, we'll be able to find interesting results. Now, this may not be easy at all. If you just go blindly, you may end up going in the totally wrong direction. And this is an example within the context of networks with something called degree-degree correlations, right? It's the idea that, you know, if I'm in a network and I have a high degree, does that mean that I have neighbors with high degree too? Or does it mean that I have neighbors with small degree? I'm assuming that everybody in here knows what degree is. And, you know, there were analyses made for many networks. And these analyses suggest that there was, in fact, a correlation between your degree and the degree of your neighbors. And this was just, I go to the data, I calculate these, and I come to a conclusion. And there were lots of papers, and I'm talking about papers written by statistical physicists, because that's where I come from, that were investigating these and trying to understand it. Well, the problem is that if you actually account for degree distribution or degree sequence, then a lot of those very strong degree-degree correlations sort of go away. So you are making people were trying to say, okay, we have these degree-degree correlations, we have to understand them. What is it caused for? Well, it's caused because of the degree distribution themselves. And you can see that once in this paper authored by Vespignani and co-workers, once they accounted for the degree distribution, these strong correlations sort of disappeared. And actually, in a subsequent paper, we actually looked at the fact that many of these networks have a community structure. So there are modules. And if you account for the fact that these nodes are organized into groups, and if you account for the degree distribution, then the degree-degree correlations essentially completely disappear. So we were looking at data, analyzing it, not thinking about null models, and we were trying to explain something that is not a relevant phenomenon. It's sort of a byproduct of something else, of the fact that networks have modular structures, and the heterogeneous distribution of degrees is going to affect the measurement of some other properties. So discovery is tricky in this context. And we cannot do successful discovery if we don't have sort of appropriate null models to see, is this result beyond what we would expect based on a few other things we know about the system. Now, understand, I think that null models provide a way to start to gain understanding about what's going on in the system. And again, understanding is really, really hard. And one of my favorite examples about our difficulty in understanding what's going on in these systems is given by this particular building, who I'm going to ask if people know what it is. So this is Biosphere 2. Texas billionaires spent $150 million, I think, in building it. And the idea was, well, if we are going to live in space, we'll need to be able to have sort of self-sustained ecosystems. I always like to point out that Texas billionaires really, have a strong belief in themselves. Because this is very interesting. So you'd imagine, I don't know very much how to do this stuff, so I'll try to make one ecosystem that is self-sustained. But clearly that was not enough. So they tried to build like 6 or 7 different ecosystems. There was a little forest, a little lake, a little desert. So let's build all of these things. And so the idea is that this would be enclosed, and sunlight would come in. There would be no exchanges with outside. Okay? So, they put the soil, they bring in the mice and the ants and the flies and all of this stuff. Let's see how it works. And the way it works is that a few weeks later, oxygen levels start to drop. The pond starts to be overrun by bacteria, by algae, and maybe this cannot be run as a closed system. Right now it's sort of an attraction for kids to learn about science and biology. But it's the point of, we know in here pretty much what the components are, but we don't know how their interactions make the system work. And the point here is that we still have very little experience or intuition about the importance and effect of interactions. This is one of the things that makes studying this system so hard, is that interactions are tricky. Special interactions that we cannot sort of write as, oh, this thing decays as the second power of the distance or something like that. The interactions that are much more non-trivial and that cannot be quantified in such a precise way, saying yes or no, or 3 times weaker than the other one. In situations like that, we have tremendous struggles. And I think this is the challenge on understanding complex systems, is the fact that we have to learn how to deal and account for interactions that can change in very subtle ways. I was going to tell you another story about how things don't work, but that's not important, and I'll try to keep to my time. But so the point is, to understand really requires appropriate null models. And again, just to give another example of something sort of misguided, if you look at things, again, without trying to understand and see, is the data really showing me what I want? One area in which this has been very relevant is in trying to understand human activity and burstiness in human activity. So there are many situations in which types of activity are not spread sort of homogeneously in time, but they come in bursts. There are periods in which not much is going on, and then are other periods in which lots of things are going on at the same time. And Laszlo, a few years ago, did this analysis for email activity. And the idea here is, let's look at the interval between consecutive emails. Okay? What is the distribution, and what does this tell us about the system? And in this particular case, the claim was that the distribution of intervals between consecutive emails was decreasing as a power law. And this was understood as saying that, well, if it is a power law, it's not a Poisson process. So if it is not a Poisson process, maybe there is some other strategy and some other mechanism that is describing what's going on and how people perform or switch between tasks. And again, you could say, I have lots of data, I can do the analysis, I can come up with a result, and this should be enough evidence for trying to build a theory that explains this particular behavior. And the theory in this particular case was priority queuing, saying that people rank their tasks in order of priority, and the way in which they tackle them is by priority. Now, one aspect that we found out when we looked at this data very systematically was the fact that when you look at it as a power law, there were some regions in which there were specific and systematic differences. So if you look at around tens of hours, systematically in the data, the power law sort of overestimated or underestimated what's going on. Now, the existence of systematic deviations like these suggests that something else is going on. And one of the things that we know is that if we have a mixture of timescales that are different enough, the mixture of them is going to look like a power law, except that at some specific regions is going to have systematic differences from the power law. So this would actually be suggesting that what is going on with the data is not something that is a power law, but it's actually a mixture of time scales. And so we are actually able to understand this data in terms of Poisson processes that have rates that get modulated in the course of the week. So in the case of emails, some people actually send emails at different rates during the week and during the weekend. That the rate is also modulated during the course of the day. You know, when you are awake, you tend to send emails, and when you are asleep, you usually don't, in spite of that ad in which the guy is typing on his BlackBerry while sleeping. And so when you put all of this together, what you find is that, you know, you find something that looks like a power law, but with these systematic deviations. Now, this is extraordinarily important, because if what is going on can be explained by a Poisson process with variable rates, the thing that we are trying to understand is why do the rates vary and how? Not, is this a priority queue and how do we prioritize tasks, right? It's a question of going in completely different ways of understanding. So even though this looks like a good power law, and you'd say, this is a parsimonious description of the data, it leads you in a completely wrong direction for explanation. So having the appropriate null models is really important. And the point is that once you have these null models and you have some understanding of what is going on, is when you are actually able to engineer the system. Now, the one about email seems very, very sort of, yeah, it's cool. People send emails, it's interesting. Actually, there are many contexts for which this system is sort of paradigmatic. It's essentially about switching between tasks. I'm either doing email or I'm not. And so at what times do I decide to switch to a task or not? And you can think about many biomedical examples in which that is relevant, right? If I have a chronic disease and I have to take medication regularly, I may have a complex medication plan. When I have to take a drug, how much do I have to take it? And again, the likelihood that I will follow that plan depends on my ability to switch from whatever I was doing to this action of taking the drug. And this is very serious in cases like mental disease. So if you are manic, then you need to take your drugs so you don't go into manic incidents. Now, because people recognize this problem, they think, well, we need to remind people about taking their drugs. But what happens when you remind people all the time about something? Especially when you remind them at times that they would recall and remember to do the task. You tune it off. you start ignoring it. Now you can think about a likelihood of remembering to take a drug. In my particular case, if I have to take it at breakfast or dinner, I'm fine. If I would have to take something at 11 a.m., I would forget it every single day. I mean, I'm doing email at 11 a.m., right? I'm not going to think about taking my medicine. Now, a system that is not aware of these and reminds me at all times would be annoying. A system that is actually aware that I will recall to take the drug at breakfast, but not at 11, and reminds me at 11 would be very useful. And I think the ability to engineer depends very much on our ability to understand in a concrete way what is going on. So, to summarize, in my last 30 seconds, did I already go over?
No.
I haven't? Oh, okay, then I'm going to tell you a story about my life. No. When I was a little boy. So I think we need science, a science off. I think we need theories off. And I acknowledge that in these areas, it's really, really difficult to build such objects. But I think the fact that we have these extraordinary amounts of data, as long as we are not doing just blind data mining, offer tremendous opportunities to understand these systems and ultimately engineer them. So that was my spiel. Thank you very much for your attention, and I'll be happy to answer any questions.
Thank you, Luis. We have two microphones that are moving. Tommy has one and Alina has the other. I know we're running behind schedule, but we need to make sure we can engage with some of the interesting ideas that Luis just put in, provocative ideas. Go ahead, Jim.
So I obviously don't disagree with the idea that we need math and theory behind some of this, and I tend to think at a certain level of abstraction your ordering is correct. But I wonder if in reality that's true. That is, it's a much more interconnected thing between the engineering and the theory, between the testing, things like that. So I think about, if I move from sort of pure biology to translational biology, for example, we knew a lot about what antibiotics did long before we had any clue how they worked, and they were already saving lives, right? So I think obviously it's simplified, but I think that this study tease apart thing needs a clearer thinking about that.
I completely agree. I mean, one of the interesting aspects is Joshua Epstein that has the saying about if you cannot build it, you don't understand it. And it's, well, yes and no. Sometimes you actually can build things without understanding them, right? I mean, we have built world economies, we have built the internet, and we have built the web, and we don't understand it. I mean, sometimes these things just kind of build themselves without us understanding them. But then that is just sort of letting things go. And so it's not like this is the only way to go and we should only build something once we have understand them. It's that worrying about the understanding piece, I think, is very important. But I totally agree with what you are saying.
One more question.
And if it was not 8 a.m., I could be much more subtle in what I'm saying.
One more question, Bob. When you identify yourself also, your affiliation?
My name is Balazs Redricks from the social sciences, and I wonder, it was a very interesting talk, and I try to translate it to the social science aspect. And for me, it seems a dynamic between discovery and testing. And it seems that with the availability of large data sets on social behavior, we have the potential to discover. But I guess in the social sciences, as opposed to maybe biology or engineering, we have to discover or imagine the system itself, or name it, or capture it, which is a lot more degrees of freedom or ambiguity. So I wonder how you see that kind of interdisciplinary dynamic if you move your ideas towards more the human social interactions and organizations.
So I'm not sure if I totally agree with your statement about biology. I think in biology, you have the same sort of ambiguity questions about what exactly is my system, what have I named my system. And I think that book, that article about how a biologist fixes the radio is exactly about that, about some trend still in biology from other traditions of sort of saying, no, we need to have this very well-defined system, and it's very clear. This is what matters. This is what I want to understand. And they have been struggling with the fact that that is not going to be really productive. And so if we now have to define what our system is and how a part of it interacts with the rest in a subtler, and it's all much more subtle, I think you get to something that is very similar to the challenges that the social sciences have been struggling with. And I think one of the reasons for interdisciplinarity is, for instance, social scientists can be really helpful to biologists in guide them through, look, you have to believe there is ambiguity in here. You have to deal with it, right? It's not, I know that you want to build a fence around this area and that will make you feel more comfortable, but that's the wrong way to go about it. So I mean, I'm a huge believer in interdisciplinarity and people talking and helping one field helping another, sort of making one of these transitions. Because it's not easy, because you have been trained all your life in a given way of thinking, and it's many times very hard to let go of it. Yeah.
Great. Well, in the interest of catching one time, we'll have to continue this conversation later on.